So we looked at both the space debris and the active satellites and the inactive satellites, and we built a baseline for 2019. And then we tried to look at the trends in launches, how different nation states behave, what they tend to launch, where do they launch those things, how long do they last on orbit, and so on. And then we had to look at the emerging technology. So the principal emerging technology are these so-called mega constellations. That's the big thing, and we all are aware of that now. So the big enablers of that is the ability to launch a single rocket body off which you peel 60-odd satellites, and then you've got to populate a single orbital plane with those satellites, spread them out, and then you launch another 60, another 60, another 60. So I dug into the FCC filings for SpaceX and for Blue Origin and for a lot of other companies too. What you can see is that in low Earth orbit, so we're talking about sort of 600 kilometers to say 1,500 kilometers off the surface of the Earth, that's the orbital altitude, there'd be something in the next 10 years, easily another 12,000 satellites populating those orbits. And that's an absolutely huge number. Now, if we can run the films when you eventually see them, it's quite shocking, actually. And everybody I've shown these simulations to go, how are we going to handle that?
Welcome back to another episode of the Cold Star Project. I'm your host, Jason Kanigan of Cold Star Technologies, and I'm here with Professor Marek Ziebart. And he's joining me from London, central London. And I'm super excited to have him on because the more I have learned about him, the more I like him. And we hadn't even met yet because he's a devotee of Richard Feynman, who I also have followed a lot and researched a lot and listened to a lot because there's videos of him on YouTube explaining stuff at Los Alamos, some kind of cool stories, and him traveling or about to travel at the end of his life to a place in like Russia or Mongolia or something like that, and not being able to do it. But he is his PhD is in satellite geodesy, which is a new field to me when I first heard about it, and astrodynamics. He's a professor of space geodesy, as you might have thought, and director at University College London. I'm going to say this phrase again, Space Geodesy and Navigation Group, which is something that we're going to explore. There's some cool pictures of it online and you've been running that for many years. He's a fellow of the Royal Astronomical Society, a journal reviewer, winner of several awards, including something called the Tycho Brahe Award, not the Tycho Brahe Prize, which I found out was a different thing entirely. This was from the Institute of Navigation. So if you are lost, he is probably someone to go talk to find out where you are. Thanks for being here.
Great to be here, Jason. Very nice to meet you too. Thanks.
Awesome. And photography. I forgot about the shared interest in photography too, because that's way down the page here. So let's explain what space geodesy is for the absolute newbie. Let's pretend that people have never heard of it before.
Well, space geodesy, it's the science and also eventually the engineering of determining the dynamic characteristics of planets. So what we mean by that, we mean things like the gravity field of the planet. We mean things like changing global sea level rise, plate tectonics, the earthquake cycle, those kind of things. And the space component of it means that we do this work by putting spacecraft in orbit around the planet and either kind of bouncing radio waves from the spacecraft down to the planet's surface and back, or by putting sensors onto the planet's surface and monitoring them from space. All
right. That is the quick summed up answer. Now, as to the actual getting this done, it's a lot more involved and more difficult than that. I watched a presentation you did way back in 2011 explaining how GPS worked. And the first thing you got into was Einstein and relativity because, well, when the satellite starts moving and the Earth starts moving, they're moving away from each other. So what goes on? Let's explain a little about GPS, I guess, and how complex this is. Why it couldn't have been done in 1920, let's say. Well, okay. So first of all, you need spacecraft in orbit.
So that's the first thing. So from 1960s onwards, then people started building platforms they could launch into orbit. And the kind of neat thing about being in orbit is that once you've got the thing up there, it just goes round and round and round, right? It stays in orbit. So gravity does a great job for us in that respect. The second thing is you need some way of ranging between the spacecraft and the Earth. And this is where the Einstein part comes in, because the way in which it is done is by using clocks. Essentially what you have is a clock in the spacecraft and you have a clock on the ground, and you send a kind of time signal from the spacecraft in orbit saying, okay, my clock reads this at the moment. That kind of flies down through space, reaches the clock on the ground, and the clock on the ground looks at that signal and says, okay, this thing was sent at 12 o'clock, and I picked it up 2 seconds later. So the clock on the ground knows the signal's been traveling for a couple of seconds. Now, obviously, it's more like a microsecond, but the thing is that the whole ranging concept between the surface of the Earth and a spacecraft in orbit is, for a great proportion of applications, is based upon using clocks and measuring the time of flight of the signal. So if you know how long the signal's been traveling for, and you know the speed of propagation, you can work out the range, because basically the speed of propagation times the time of flight gives you the distance. Now, all that would work out fine.
Right. Except
because of things like relativistic time dilation. And so Einstein's ideas explained that if you had a clock in orbit, whizzing around in space, and it's at a different gravitational potential, it's not on the surface of the Earth, then the clock's going to behave in some strange ways. So actually, things like GPS rely upon relativity as it's the bread and butter of how these things work. If we didn't apply relativistic concepts, you just couldn't navigate your way down to the corner store. You might be able to find your way to another city, but you would not be able to very quickly, park your car automatically, with your Tesla.
Right. Yeah, and folks can remember even from high school, no matter what level you got to, I'm sure you remember the relationship between speed, distance, and time, right? And we know a couple of those factors here, right? So we could figure out the distance. And I remember from your talk, it really struck me the time difference because of the relativity might be something really tiny, a fraction of a second. And yet, if you didn't account for it, the distance was off by like 11.5 kilometers or something, I think you said. So
you definitely, Jason, I can tell. That's right.
Yeah.
That's the drift after about a day. And so if you didn't take that into account, it would get worse and worse and worse. So actually, there's an interesting story about this, because when the US Air Force first commissioned all this stuff, the Air Force were great drivers of innovation in that respect, but they weren't necessarily convinced that if you put this clock up in space, that the relativity would really make that much of a difference. And so they demanded that, up front, the system could be designed so you could turn off these relativistic effects if Einstein was in fact wrong. But, as it turns out, not all of Einstein's ideas, but, the first order relativistic ones, we couldn't get by without them. So, people like me use that kind of stuff on a daily basis. And ironically, so does everybody else now. We all rely upon those relativistic concepts.
All right. Now, I remember at the end of that talk, you said, please don't ask me any hard questions, but I might now, the one that struck me is, so with this Space Geodesy, you are measuring the impact of photons on satellites, right? Which will be pushing them around. And the thing that strikes me is I've been studying physics and chaos theory and that since I was about 19 years old. We had a 3-hour break at our college classes on Wednesdays, and I used to go study stuff, being a nerd, instead of going outside or something like that. Right? So if photons have no mass, how is it that they're pushing around satellites?
Yeah, right. Okay. So most people these days know E equals mc squared. Right? That's the fundamental relationship between energy, rest mass, m0, and c, the speed of light in vacuum. But actually, a more complete version of that formula is E squared equals m squared c to the 4 plus rho squared c squared, where rho is now the momentum of the particle and c is speed of light in vacuum. So even though a photon has a rest mass of 0, it still possesses momentum. This is one of the ideas that Einstein suggested. So even though it has no mass, it still has momentum. So when a photon pings onto a spacecraft, it imparts a tiny little push. And when a photon leaves a spacecraft, like emitting some heat or a radio wave, as that photon leaves it, there's a recoil force. It's Newton's equal and opposite reaction force.
Right.
So again, that sounds very esoteric, and you might think, well, what possible difference could that make? But I've built much of the last 20 years of my work with the Air Force and with NASA and the European Space Agency on the fact that photons push stuff in orbit.
Wow. So you have added to my physics knowledge today. I hadn't heard of the the deeper level theory that has been worked out. Yeah. So in your LinkedIn description, in your kind of summary of who you are and what you do in that, you mentioned very early on this thing called antenna thrust. And so I was like, what is that? Because I'm curious, and I started Googling around and I found something called thrust bearings. But I really have no idea what this is. So what is an antenna thrust and why is it important to you?
Yeah. Well, let's start with how you figure out where a spacecraft is in orbit. When you want to calculate how something is moving in space, then a major part of that is to write down equations that describe all the forces that act on the spacecraft. And so, there's a procedure called integration in mathematics, numerical integration, where you essentially, if you've got a differential equation that describes how something is changing, you can determine the state of the thing itself by integrating those equations. So where orbit determination of the spacecraft is concerned, you try and write down equations describing all the forces, and then you integrate them twice to get position. So the derivative of position is velocity, derivative of velocity is acceleration, scale the acceleration by the mass, and you've got the force. So we start with equations describing forces, and we end up figuring out where the thing is in space. So the better you can write those equations, the more accurate those equations are, the better you can work out where the spacecraft is. So we need to figure out all of the significant forces acting. So we've already established that photons, leaving a spacecraft in the form, say, of a signal, a transmitted carrier wave, for example, because the satellite's doing some ranging and wants to transmit the signal down to the Earth, which we pick up. So the satellite is kind of pumping out this energy. So for a GPS satellite, for example, they throw out about 100 watts of energy. So, think of a 100-watt light bulb on a satellite 20,000 kilometers away, 3.5 times the radius of the Earth out in space, and it's shining down at 100 watts. That's the energy in the carrier wave signal that carries all the information that we use for GPS. Now, the thing is, because those photons are systematically pushing down towards the central mass of the Earth, that means there's a recoil force in the opposite direction on the spacecraft. And that's what we call antenna thrust. And it wasn't an idea that many people took seriously, but now, for example, all of the scientific processing of GPS satellite orbits that's done by the Jet Propulsion Laboratory and MIT and those kind of people, they take into account this effect because it's systematic and it shunts the satellite's position in space.
Okay, so it's yet another factor that needs to go into those calculations to figure out where your satellite's going to be, because it's literally pushing itself away. Interesting. Okay, so there's the Space Geodesy and Navigation Laboratory at UCL, and you've been running that for a long time. Did you create that, or was it already existing?
There was when I first joined UCL, I joined a group that was working primarily on sort of GPS technologies, and then as I became a bit more senior, I sort of essentially built the group myself from a certain point forward in time. So yeah, so it's my, I don't know, offspring of some kind. Yeah.
Right, and obviously been around since before 2011 because you had pictures of students and that in there. And there's, I guess, graduate students or PhD students rolling through this thing?
Yeah, that's right. So it's a kind of standard common or garden university research group. So it has academics, a few professors and associate professors and assistant professors, has postdocs and has PhD students, and then sometimes master students will do their dissertations with us, that kind of thing. So generally it's centered around various applications of space technology. So there are lots of problems in the science and engineering domains that rely upon space technology. We kind of work on those, and we work with space agencies, governments, the military, and commercial companies.
Okay. If you want to talk about a project or two that you have the approval to talk about, because I'm sure there's security and compliance issues in that'd be great. Give us a flavor.
So I mean, things going on right now. So we're working on Galileo, which is a European sort of version of GPS, which that's primarily with the European Space Agency. So that's working on dynamic models for those spacecraft. And we have a project with the US Air Force, which is called Track Custody Geo, which is all about trying to identify and follow the trajectory of your own very expensive assets that you've got flying around, in the communication satellite belt, which is about 36,000 kilometers away. difficulty there is that things are far away, and the primary way you've got of observing them is with a telescope.
Mm-hmm.
So you have these little bright dots in
Right.
your field of view of the telescope, and you want to know, is that bright dot, is that my bird there? And that other one that I see maneuvering over there, is that doing something nefarious, or is it moving in that way just because that's a natural trajectory? So why that's important is because at some point, if somebody is doing something, if there's a bad guy out there, you want to figure out, are they doing something deliberate, or is that just, am I seeing something unfolding and I'm misinterpreting it? At some point, somebody's got to phone the president and say, do something about this.
Okay, so a little scary. Yeah, and it's like basic things like the difference between detection and tracking, right? This is something that I picked up from Dr. Marie Majah, which sounds so straightforward, and you don't really think about it unless you're involved with this stuff every day. And there have been a couple of companies. Clinton Clark was a guest who I had on. That's with the company that does high altitude detection, and they're watching all the time with telescopes and that. So I am curious. We've talked about this, and you just mentioned it. You're doing spacecraft orbit determination and prediction and measuring of GPS data. So what kind of data and tools are you using to be able to collect and process this stuff? Because you don't have your own telescope network, I imagine, or data science department like we do.
So for what we do, there are two kinds of data, so to speak. There's data about the spacecraft themselves, structural information, what it's made of, what the materials are, what they're flying on the spacecraft in terms of instruments, how its attitude is controlled. And you could also say telemetry from the spacecraft, which comes down, tells you stuff about, where is it, what's it pointing at, how hot are its instruments, those kind of things. We use all that in the process of building these equations that help us, predict and model satellite trajectories. The second thing is various forms of ranging, which are carried out from the Earth to the spacecraft, or from the spacecraft to the Earth, those kind of things. So those are measurements. Now, we can get measurements directly from a telemetry stream from the spacecraft. So we have some arrangements with commercial companies,
the operator,
and the data comes straight in. Or there's a big organization called the IGS, International GNSS Service, which is run out of NASA JPL. Its job is to run big networks of permanently occupied tracking facilities, and they pull data down and make them available in quasi real time, actually, from these big networks all the way around the Earth. So there are actually thousands of these tracking stations, and such data is actually publicly accessible to almost anybody. And as a resource for research, it's relatively untapped. So I'm on the governing board of the IGS, and I'm the governing board of a similar organization called the IDS, which is the International Doris Service, which is the French Space Agency's satellite tracking system. So
and so that's where the data comes from. Right. And so the students in the lab are doing the data processing, or do you have a kind of a continuous program, I guess, set up for doing that that's been operating for years now?
Yeah. So we've mostly built our own in-house software, which is kind of coded in C++, and we've built that from scratch from a long, long time back. And we kind of add to that periodically. But we do use other people's tools sometimes. One important distinction about my group is we don't do operational work. So we don't do work on a day-to-day basis where somebody is like waiting at like 4 o'clock in the morning and going, have you processed today's run? So we develop mathematical models, which we then provide to people like the Jet Propulsion Laboratory, and they then use what we produce in their operational work.
Okay.
Which is scary. It's scary because when you're the big,
you don't want to get it wrong.
Exactly.
Right. Now, I have interviewed a fellow, and this episode has not come out yet as we're recording this, but it will be coming out this Thursday, so it'll be out by the time our episode comes out here. And I interviewed Luc Maisonneuve, who's with Orikit and CS in France. And so I'm curious, this is a dumb question from my dumb perspective, right? What is the difference between a low-level dynamics platform like ORCID and what you're doing?
Okay, so it's horses for courses, right? So, if you just want to design a mission, to do something fairly crude, you just want to know that it's going to have a repeat pass over the Earth at a certain, then you can get away at design stage, even with, say, a Keplerian model, which just means that the two-body equations. The Earth is a point mass and satellites in space, and you can learn an awful lot. And to be honest, that in itself is quite complicated. However, the scientific requirements of many missions now are actually to know where the satellite is in space at the level of a few centimeters, or even down to 1 centimeter, or even try to get below 1 centimeter accuracy in space. Now, that might seem a crazy proposition, but if you're measuring, for example, global sea level change over decades, then you need that level of orbital accuracy. So it's all to do with how hard you're trying. So if we to try and put this in perspective, if we were to actually sort of put down on paper the equations that we started writing these equations down, then you'd still be writing 500 pages later. You'd just have an immense amount of information. So, for example, if you're doing sort of a GPS orbit prediction, and it's done very, very detailed dynamics these days, that level of sophistication is what's in the operational software. So, again, it might seem crazy going, why do we need to know where a GPS satellite is at the centimeter level? But in fact, we rely upon technologies like GPS to define what we call the global reference frame. So there are various things like measuring sea level change that require us to have a coordinate system on the Earth that can measure these tiny signals. And so things like GPS support what we call a reference frame. You can think of it as a coordinate frame if you like. So plate tectonics, the earthquake cycle, monitoring volcanoes, all those require this very, very precise scientific measurement system, and GPS is part of that.
Okay, and you cannot get that level of detail from ORCID.
Okay, I'm not going to say what ORCID.
Okay.
I mean, but the thing is that the software libraries to do all this stuff are pretty broadly available. Like, my group, we work openly. So if people want to upgrade their software to something much more sophisticated, we tend to share that stuff freely.
Okay. Yeah, you know what capabilities you have, so you could speak to that. All right. Let's get specific here. Then I've got a question here about, you worked with the ESA to develop force models for the Galileo and Sentinel-1 missions, and so I'm curious how the force models you developed impact the success of missions like those.
Okay, so we just had our sort of final technical meeting for that project. That's a 5-year project with the European Space Agency, and I can't really say how successful it was, except that I'll just go, it was that successful, right? So the aim was to try to get to sort of sub-centimeter orbital accuracies. So what I can say is we computed 2 years of orbits for every satellite on orbit. So there's about 20 odd satellites, 20 years. We checked the accuracy of those computed orbits using lasers, firing lasers from the surface of the Earth, and over the 2 years, we are achieving an orbital accuracy of around about 1 centimeter for the entire constellation.
Okay. You can't afford to be second best. You need to be first, and that requires speed. Now, if you're thinking that growth is supposed to be slow and steady, frankly, the way I was taught back in the 90s in the operations management and business administration programs, you are too slow. We have to adapt. And in space, it's no different than anywhere else. People like to think they're special in space, and it is fun, all the stuff we get to work on, but business is business. The fundamentals nowadays are conservative growth is not good. You need to run as fast as you can and risk outstripping your supply lines, which means in our world, using up the capital that we've got. That's a risk. But there is no prize for second place. There certainly is no prize for third. If you want to scale operationally fast, come talk to us at Cold Star Tech. We are the process experts for scaling fast. Now back to the interview. What do you
So,
find is like the limiting factor for you for data collection or accuracy? Like what are you waiting on usually?
yeah, so for many years, it was to get sufficiently detailed information about the spacecraft itself.
Hmm.
It used to be that people were very cagey about
Huh.
saying, okay, we've got this amount of, this grade of MLI, which is a
Hmm.
multiple layer insulation on the spacecraft. People were apprehensive about telling you that because they didn't
Hmm.
want the radar profile of their spacecraft to be revealed, that kind of thing. So we've had various we're now much closer to the various space primes, and we have a good relationship with them, and they will give us the information. We'll then compute the models, which are just a set of equations, which
Hmm.
can't be reverse engineered to reveal the structure of the spacecraft.
Okay.
But that took years to kind of get there. So we're past that now, and so people like the European Space Agency are much more open to working with us because they want to achieve these, you could say extreme levels of orbital accuracy.
Hmm.
So that's one limit then, is always knowing enough about the spacecraft, right? And we're kind of past that now. It's a long fight, many years. Then finally get to the problem of how do you determine what is this orbital accuracy? You end up going, well, how do we know that we've done as well as we think we've done? And we do that by firing these lasers at the spacecraft. There's a whole series of stations around the Earth, which are called satellite laser ranging stations. And they've got a ranging precision of about 2 to 3 millimeters. So these guys can fire a laser from the surface of the Earth, and they can range to a spacecraft that could be, 30,000 kilometers away, and they can determine that range to a precision of 2 to 3 millimeters, which is crazy, but they do it.
Right. That ray is just not diffusing very much. It's just going right out there.
And those people have been, that kind of technology has been in development by, supported by NASA and agencies around the world for decades. So it's been a long time in the making, and it's a part of this whole network of infrastructure, spacecraft on orbit, space agencies, universities, who all work together to achieve the science that comes out of this. So it's a great human collaboration story, actually.
Mm-hmm. But it's to get people to relax and go, look, everyone can see everything else now. We know what it is, what that's up there, and maybe we don't need to know everything about what it's made out of. I like the reverse engineering is not possible. I think that is a very relaxing thing. So I'm going to read this question out because I want to make sure I get it right. So you were a principal investigator on an ESA project to design a combined navigation and communication system for manned and robotic landings on Mars. That sounds like a lot. That's a big scope. What outcomes did you reach that you can discuss, and what was maybe the most challenging or surprising element of that project?
Yeah, well, first of all, it's an amazing project to win. It was just wonderful to do that. And I think maybe the first thing is that when you get into a project like that, you have these preconceptions about what you think the problem's going to be and what you think the nature of designing a system like Mars is. Then 3 months in, you learn so much so fast. It's quite incredible. I remember looking back at our proposal document and going, I can't believe we won that, but there we go. Come the other side. So first thing, simple thing. So the ambition is to have pressurized vehicles landing on Mars, where a couple of astronauts get into that pressurized vehicle and they kind of drive 10, 20, 30 kilometers away from the landing base. So the first thing is how far do you have to move from the landing base before you can't see it anymore over the horizon? In other words, what's your line of sight? So one of the first things we did was worked out if an astronaut is standing on the surface of Mars, and let's assume that it's a spherical planet with even terrain, then how far can they see? And actually, in imperial units, it's about 2 miles. It's about sort of 3.4 kilometers, which is not far at all.
Yeah.
So the point is that very quickly, all your points of reference are over the horizon. And so you need ways to have some way of determining where you are. Now, there's a great story behind this, actually, which is that in one of the late Apollo missions, when they first had a rover, they took it to the edge of a crater, They went down into the crater, and they were, collecting some samples, and then they had to walk back. And there's this moment of panic when one guy looks at the other and goes, "Which way was it back?"
Right.
Because in a crater, you just see the rough
edge,
and you can't see where the rover vehicle was. And so they had to make a call because it was a hard regolith. They couldn't see footprints, and they just had to make a guess about which way was back. So, we were told all this when we started the project, and it was like a sense of going, wow, there's a high level of responsibility here. I guess the second thing that we learned about it is that it's how to make a system resilient and redundant and reliable. Because with all these engineering things, stuff goes wrong, and whenever you do anything in space, you learn that what you thought was going to happen certainly didn't happen the first time, and so you need a resilient system to do that. But having said that, we had access to this high-resolution stereo camera terrain model of the landing sites, and we sort of used that to work out where we could put beacons on the surface, and we sort of simulated what we call the bit loss error rate. So you're transmitting a signal from these beacons you're using for ranging to work out where you are, and we used tools that are designed for mobile communications on the Earth to simulate that on Mars. So we worked with a company called British Aerospace here, by the way. They did the communication part of it, and they were very, very smart guys, very, very experienced. That made a lot of it easy for us. So perhaps maybe it's worth saying what was the basic navigation technology that we designed for all this, and that was based upon micro-miniaturized atomic clocks. So when we did that project, NIST they're in Colorado, right? They had just done some characterization of these tiny little atomic clocks. Now, we've already talked about how ranging is based upon timing. So the idea was to have these micro-miniaturized clocks inside the beacons, which are transmitting the ranging signal, and the astronauts are wandering around with bits of kit on their rover vehicles and on themselves with a clock as well. And they're using those signals going between the two to help measure their ranges. But the but is that you've got to calibrate the drift of the clocks. Now, we can do that with GPS in a very straightforward kind of way, but when you're on Mars, it's different. Right. So what the European Space Agency gave us a budget and said you can have 1 or 2 orbiters in space. And so what we did was we kind of calculated the way in which the clocks would behave based upon the NIST characterization of the clock, and then worked out a design of the orbits of the spacecraft going around Mars so that periodically you could do time transfer between the central base and the people in their own where they were. And that meant you could reset the clocks periodically and keep them within specification. But that was all, it was really interesting. Yeah, of course it was challenging, right? Yeah. It was challenging, but we know a lot about Mars now. Interesting things are, for example, there's no magnetic field, right? You can't have a compass, right? And you might be in a dust storm, and you might be in some very, very crazy terrain. Something like Holden Crater is quite flat, and some of the plains are really flat. But some of the places where we want to go, they're like the Grand Canyon plus. So it's a tough environment, without a doubt.
Right. Wow. There's a lot that went into that project. The first thing I was thinking of is you need a way of leaving breadcrumbs so that the astronauts could find their way back, or you need a GPS system for Mars, which is kind of the approach you went. And there are some points of failure in that too, the solution, right? If something breaks, if the orbiter breaks, you're going to drift, right? The timing is going to drift. So that is complex.
Yeah.
What is the next step after that then? Do they have to come up with a mission to actually make products like that to send there with astronauts and a rover, and it all, I guess, becomes this huge expensive project?
Well, the thing is, these things have huge lead times. Such things are planned many, many years in advance. So a project like that was aimed at launches between 2030 and 2040 for those kind of missions. So there's a lot of future scoping goes into this. It's looking at, as part of the project, we looked at various quantum technologies, for example, that were starting to emerge, and say, okay, so 10 years from now, what level of technology maturity will there be? But also, there are some people who their job is actually future scope requirements emissions, and then to actually encourage commercial companies or research groups to develop such technologies. So sometimes you just have to think in an imaginative way, going, what would we like, or what are the requirements? And some of it just looking at trends in technology and saying, well, like quantum is a huge thing these days, and there are lots of big things that are said about quantum. We were there with things like nanotechnology before. We were there with cold fusion before. So there has to be a certain hard realism that goes into it as well, and say, okay, what's the baseline technology that we feel we can guarantee?
And then try and build out a bit from that. Yeah. And there might be some great discovery, but banking everything on that is kind of a dumb idea. So let's move into space situational awareness and sustainability here. Just before we started recording, we got on and looked at a couple of simulations that you were showing me, and we'll try and embed those. I'll either have screenshots or the video itself that will overlay over this. It was like kind of what I've learned to expect now, but also kind of crazy at the same time to really see this. You recently completed this study for a DSTL on future space populations, and you predicted it out over the next 25 years. So we're looking at simulated launches of these mega constellations. Tell us about that. How did it work? What did you discover? And we'll show this on the screen as well.
Yeah. Well, so the first thing we did was have to essentially review all the catalogs. A catalog in this business is essentially a list of missions, when they were launched, when they failed, are they still in space, are they active, are they inactive, who owns them, roughly speaking, what do they do. So we reviewed all the catalogs of everything in space from like 1960 up to now, and then we built a sort of baseline catalog, because there's lots of conflicting information in these things, by the way. It's not the case that you can just trust. You can pick up a bit of data and go, okay, that's real.
A Jonathan McDowell might have a pretty good catalog there, but yeah.
But it takes a fair effort to do that. So we looked at both the space debris and the active satellites and the inactive satellites, and we built a baseline for 2019. And then we tried to look at the trends in launches, how different nation states behave, what they tend to launch, where do they launch those things, how long do they last on orbit, and so on. And then we had to look at the emerging technology. So the principal emerging technology are these so-called mega constellations. That's the big thing, and we all are aware of that now. So the big enablers of that is the ability to launch a single rocket body off which you peel 60-odd satellites, and then you've got to populate a single orbital plane with those satellites, spread them out, and then you launch another 60, another 60, another 60. So I sort of dug into the proposed, what called the FCC filings, the Frequency Control Commission, I guess, something like that. They're the people in charge of saying, okay, you want to launch something and you want to operate at this frequency, we're going to give you this bit of bandwidth, and you've got to operate in that. So people who want to do this stuff have to show their hand a little bit and say, okay, we want this many satellites operating at this power and at these frequencies in these orbits. So I dug into the FCC filings for SpaceX and for Blue Origin and for a lot of other companies too. What you can see is that in low Earth orbit, so we're talking about sort of 600 kilometers to say 1,500 kilometers off the surface of the Earth, that's the orbital altitude, there'd be something in the next 10 years, easily another 12,000 satellites populating those orbits. And that's an absolutely huge number. Now, if we can run the films when you eventually see them, it's quite shocking, actually. And everybody I've shown these simulations to go, how are we going to handle that? Because there's a space traffic management problem, and there's the problem of satellites becoming disabled and spinning out of control. And so one of the really interesting things is we also simulated the debris field out for the next 25 years as well. And so we had to do various simulations of how a satellite breaks up and how debris scatters. And one of the first order things we got out of that is that space debris tends to do two things to first order. One is when a satellite breaks up, the debris stays in the orbit. So the satellite's going around doing this, it's got all that momentum, right? And so that momentum is conserved in those bits. But the second thing, because as the orbital plane kind of gradually moves around the Earth, the debris spreads out into the shell. So the two things happen as debris goes into the orbit and then into the shell. Now, all these design constellations, these mega constellations, they're shell constellations. So if we start getting collisions in those shells because the traffic's being mismanaged, it's going to populate those shells with lots of debris. Now, we have a problem with debris now, but the problem of debris then may be much more serious. Mm-hmm. And there is a thing called the Kessler syndrome, which admittedly is something of a horror movie. Yeah. But the Kessler syndrome does say that once these things start banging into each other and break up, those bits hit other things, and then you get a cascade going out.
Right. Right. Yeah, and that was one of the first things I learned about in space traffic management. And a former head of the Space Development Agency told me I am not afraid of a Kessler syndrome. So that made me feel a little bit better. But when you see all these dots up there, and all these pieces, all I could say is thank goodness for conservation of momentum and things kind of staying in the same place. So very, very cool. Let's finish up with a couple of fun questions here. You and I share an interest in photography. I'm curious what equipment and subjects you most enjoy working with.
Okay, so I love photography for sure. Right? And I partly because the technology is so good these days. And you buy a camera, it's just extraordinary what it can do. So I kind of experiment with micro four thirds, and so most of my kit is in that kind of area. I have some beautiful glass, some Leica lenses, and I kind of learned that one of the really powerful things in photography is just buy a good lens, right? You will not be disappointed by spending money on a good lens. I live in central London, so a lot of my photography has to be the sprawling metropolis. But so I've learned a bit. I was in New York last summer, first time in my life in New York. Wow, what a place, wonderful place. And I'm really so deeply sorry for the citizens of New York at the moment. It's terrible. But my God, what a city, and what a photogenic city it is. I remember taking some pictures from the top of the Metropolitan Museum, looking over Central Park. That's a great vista. Yeah. But apart from that, I also kind of experiment with macro photography a little. Now, again, a really nice lens and just getting up close to plants and textures and insects, those kind of things.
Yeah, how about you, Jason? Fascinating, isn't it? Yeah, I've got the same kind of thing. Canon, Sony, mirrorless, micro four thirds, and then the old school DSLR. And yeah, my stupid money expenditures are on legacy lenses because I don't mind manual focus at all. So I tend to do that. And I started out really interested in zoom, and then over time your tastes change a little bit. So I backed out and I started learning wide lenses, and I've gotten away from that. And I did quite a bit of macro as well. With bugs and things like that. We had an arboretum in Wilmington that we could go to, and you'd usually get some interesting bugs there. And if you have a fast enough ability to focus, you'll be able to get some good images. So I had a lot of fun with that. I haven't done much in Asheville, but then again, it's springtime now, so I'll probably be out again. But I appreciate that. We're both Richard Feynman fans as well. My favorite stories from him are from those Los Alamos days where he was good at lock picking and safe cracking and that, and he'd go and break into somebody's safe and steal their papers or add something in there and that. I'm wondering if you have a favorite Feynman story as well.
Yeah, I mean, curiously, one of my favorite Feynman stories is more about his impact than the man. I mean, he's a fascinating man, an amazing guy, great scientist, and most people who've had some experience in physics have read the Feynman book, Physics Lecture Series. I mean, brilliant exposition. But there's a nice story about a guy who I think he lived in somewhere like Hong Kong, and he was a physicist, and he'd got Feynman's red books. And at that time, there's a lot of tension between the Mao regime and the West in Hong Kong. And so you get these guys stand on the border in green uniforms, waving Mao's little red book. This guy, who was a physicist, he went up to the border one time, took a bunch of his students with him, or some friends, and they took Feynman's lectures on physics, which are also red, and started waving them in the opposite direction to say, okay, here's another way of thinking about the world.
Mm.
He was,
Very,
he was
very good.
Yeah, he was a fascinating guy, and I also like the way with Feynman in that he dedicated his life to science. He was a journeyman in science, and he also perhaps the thing about him is that it was his ability to explain concepts.
Mm-hmm.
And I want a really great test from Feynman that I've tried to adopt is that he said if he can't explain something to a layman about what he's doing, that means he doesn't understand it himself properly. It's not the other guy's fault; they don't understand it. It's the failure is in the person who thinks they understand it. So I don't know how I came across in this podcast, but I do try to work hard because I find that if you really understand something, then you can explain it clearly to somebody else. And people shouldn't be daunted by professional scientists. If they don't understand what the scientist is saying, they should think, okay, maybe it's the problems with him, not with me.
Right, right. And I think, based on today and the 2011 lecture that I watched, yes, you've succeeded in being able to explain complex subjects in a straightforward manner that even this idiot can understand right here. So, right. Well, my guest today has been Professor Dr. Marek Ziebart, and he is the Professor of Space Geodesy and Director at the University College of London. Thanks for being here.
Great, Jason. Very nice to meet you. Great talking to you.
This is Jason Kanigan from Cold Star Tech. Thanks a lot for listening to this episode. I hope you enjoyed it. If you do want to get email notifications of upcoming episodes or episodes that have just been released, and maybe a little news sprinkled in here and there, you can sign up for email notifications at coldstartech.com/MSB. That's short for Make Space Boring. That's another little show that I do. It's once, twice, 3 times a week, something like that. Anytime there's news or an update on who I'm meeting and what I'm studying in the space field. So you can go check that out. On the YouTube channel, I can do something that I cannot do on Anchor for the audio only side of things. The YouTube channel allows me to have playlists, and so you might want to go to the channel, the Cold Star Tech channel, and check out those playlists, because you will find you can go down a rabbit hole basically into several areas like space law and policy, small sats, and I think that's a lot easier than trying to scroll through 130 episodes or something like that, looking for the thing that you want. So I recommend going and checking that out. And remember, if you're ready to take your space business to the next level, or you're a VC looking for deep and very valuable insight into a space company you're looking at investing in or investing further in, come and talk to us. Thanks for listening.